Hello everyone and welcome to Sally and Bytes. Today, I am here to teach Functions in Python, Part 8, for the Class 12 students of Computer Science. In this video, we are going to learn Recursion, how recursion works. Recursive function to implement the power function, sum of n natural numbers using recursion, Fibonacci series using recursion, factorial of a number using recursion, binary search in arrays or lists using recursion, recursion versus iteration, visualization and practical implementation. So, let's dive in and get started. The statement, "In order to understand recursion, one must first understand recursion," is a playful and somewhat paradoxical phrase often used humorously to describe the self-referential nature of recursion. In its simplest form, a recursive function is one that calls itself. Let me try to explain with an example. Let's use a fun and relatable example of counting the number of chocolates in a box using recursion, chocolate and recursion, the magical box puzzle. Imagine you have a box of chocolates, but you don't know how many chocolates are inside. You want to find out the total number of chocolates, but you can't count them all at once because there are too many. So, you decide to use recursion to figure it out. Now, look at this picture. Step 1. Open the big box, which I have highlighted in red box, under Step 1, and you see there are smaller boxes of chocolates inside. Boxes inside of boxes. Each small box might have chocolates in it, too. Step 2. Take the first small box and open it. Now you have a new box in your hand. Open this new box, and you find more small boxes inside. Each of these boxes might have chocolates too. Keep doing this until you find the smallest box that you can open, and inside, you see the chocolates directly. In Step 4, you opened the tiny box. You can see, I have highlighted in red box and the smiley is pointing to it. Now, count the chocolates in the tiniest box. That's easy. Now, close the tiniest box and add up the number of chocolates you counted with the chocolates in the small box you opened just before it, in Step 3. Close that small box and add up the chocolates inside it with the chocolates in the bigger box you opened earlier, in Step 2. Keep closing the boxes and adding the chocolates until you've reached the first box you opened, in Step 1. Ta-da! Now you know the total number of chocolates in the big box. This is recursion in action. By breaking down the problem into smaller boxes and counting the chocolates in the tiniest box first, you were able to figure out the total number of chocolates without counting them all at once. It's like solving a puzzle step by step, making the task much more fun and manageable. Now look at the pseudocode. In line 1, this pseudocode represents a recursive function count chocolates in box that takes a box as input and calculates the total number of chocolates in that box. In line 2 and 3, it checks if the box is a tiny box, base case, with chocolates directly, in which case it returns the count of chocolates in that tiny box. In line 4, 5, 6, 7, 8, and 9. If the box contains smaller boxes, recursive case, it iterates through each smaller box, calling the count chocolates in box function recursively on each of them and adding the counts together to get the total number of chocolates in the big box. Line 12, 13, and 14 is the example usage, which demonstrates how to find the total number of chocolates in the big box using recursion and then prints the result. Please note that this pseudocode is a conceptual representation and not a specific implementation in any particular programming language. It aims to demonstrate the logic and structure of the recursive solution to the chocolates and nested boxes problem. I hope this description helps you visualize the recursion example with the box of chocolates. So, what is recursion in Python programming? Recursion is one of the most powerful tools in a programming language. It is a function calling itself again and again. Recursion is a programming technique in which a function calls itself to solve a problem. In other words, it is a method in which a function calls itself one or more times in its body. This picture shows the working of a recursive function called recurse. It is a function calling itself again and again. Let's see the conditions for implementing recursion. Base case. Recursion requires a stopping point, called the base case, which represents the simplest form of the problem that can be solved directly without further recursion. Recursive case. In the recursive case, the function calls itself with modified parameters, allowing it to break down the problem into smaller subproblems to be solved. Convergence towards base case. The modified parameters in each recursive call should move the problem closer to the base case, ensuring that the recursion eventually stops. Repeated subproblems. Recursion is effective when the problem can be divided into smaller instances of itself, allowing the function to solve these repeated subproblems efficiently. Proper function invocation. To achieve the desired outcome, the recursive function must be called with the appropriate parameters for solving each subproblem accurately. No infinite recursion. Care should be taken to avoid infinite recursion, where the base case is never reached, as it can lead to program crashes and errors. Efficiency considerations. While recursion can provide elegant solutions, it may not always be the most efficient approach due to redundant function calls. In some cases, using iteration might be more efficient. Advantages of recursion. Recursive functions make the code look clean and elegant. A complex task can be broken down into simpler subproblems using recursion. Sequence generation is easier with recursion than using some nested iteration. Disadvantages of recursion. Sometimes the logic behind recursion is hard to follow through. Recursive calls are expensive, inefficient, as they take up a lot of memory and time. Recursive functions are hard to debug. Let's learn how recursion works. Recursion is implemented by dividing the recursive problem into two parts. Termination part or stopping point, that is the base case, for the smallest possible problem, when the function returns a value directly. Recursive part, that is the recursive case, which contains one of the more recursive calls on smaller parts of the problem. Let us write a recursive function to implement the power function. The power function is used to raise a base number to a specified exponent. For example, power of 2, 3 should return 8, because 2 raised to the power of 3 is 8. We can implement the power function recursively using the following logic. Base case, if the exponent is 0, the result is always 1. Recursive case, for any other positive exponent n, the result is obtained by multiplying the base with the result of the power function called with the base and n-1 as the new exponent. Let's see an example for the recursive Python function to implement the power function. In line 2, the function power takes two parameters, base and exponent, representing the base number and the power to which the base is raised, respectively. In line 3, in the function, we have a base case to handle the scenario when the exponent is 0. When the exponent is 0, any number raised to the power of 0 is always 1. So, if the exponent is 0, the function returns 1. In line 6, the recursive case handles the situation when the exponent is not 0. In this case, we return the result of multiplying the base with the result of calling the power function again with the same base and exponent -1 as the new exponent. In the recursive case, the function keeps calling itself with a reduced exponent until the base case is reached, that is, when the exponent becomes 0. The output of 2 power 5 is 32 and 2 power of 10 is 1024. Let's see the example to understand how the recursive power function works. Example, power of 2, 5. The function is called with base equals 2 and exponent equals 5. Since exponent is not 0, the recursive case is executed. We return 2 * power of 2, 5 - 1, which is equivalent to 2 asterisk power of 2, 4. The function is called again with base equals 2 and exponent equals 4. Again, the recursive case is executed, and we return 2 asterisk power of 2, 4 minus 1, which is 2 asterisk power of 2, 3. The function is called again with base equals 2 and exponent equals 3. Again, the recursive case is executed, and we return 2 asterisk power of 2, 3 minus 1, which is 2 asterisk power of 2, 2. The function is called again with base equals 2 and exponent equals 2. Again, the recursive case is executed, and we return 2 asterisk power of 2, 2 minus 1, which is 2 asterisk power of 2, 1. Once more, the recursive case is executed, and we return 2 asterisk power of 2, 1 minus 1, which is 2 asterisk power of 2, 0. Now, the function is called with base equals 2 and exponent equals 0. Since the exponent is 0, we hit the base case, and the function returns 1. As the recursive calls unwind, the function evaluates the multiplication operations. 2 times of, 2 times of, 2 times of, 2 times of, 2 times 1. And finally, the result is 32, which is the correct value of 2 power 5. This is the beauty of recursion. By breaking down the problem into smaller subproblems and leveraging the return values from recursive calls, we arrive at the final result. However, it's important to ensure that there is a proper base case to terminate the recursion and prevent infinite loops. Let's see some more examples of recursion. Example 2. Write a function to calculate the sum of n natural numbers using recursion. Let's understand how this function works. In line 2, the function sum of natural numbers takes an integer n as input, representing the number of natural numbers to sum. In line 3 and 4, if n is less than or equal to 1, return n. This is the base case, that means the termination part, when the function returns a value directly. In this function, when n is less than or equal to 1. If n is 1 or less, it means we have reached the smallest natural number. In this case, the function simply returns n, which will be either 0 or 1, depending on the input value. In line 6, the recursive case handles the situation when n is greater than 1. In this case, we return n plus sum of natural numbers of n minus 1. In the recursive case, the function keeps calling itself with a reduced value of n until the base case is reached, that is, when n becomes 1 or less. So when you enter a number 5, the output will be 15. Let's see how sum of n natural numbers using recursion works. The function call sum of natural numbers of 5 is made with n equals 5. Since n is greater than 1, the recursive case is executed, and we return 5 plus sum of natural numbers of 5 minus 1. A new recursive call sum of natural numbers of 4 with n equals 4 is made. Again, n is greater than 1, so the recursive case is executed, and we return 4 plus sum of natural numbers of 4 minus 1. Now, another recursive call sum of natural numbers of 3 with n equals 3 is made. The recursive case is executed again, and we return 3 plus sum of natural numbers of 3 minus 1. A new recursive call sum of natural numbers of 2 with n equals 2 is made. The recursive case is executed again, and we return 2 plus sum of natural numbers of 2 minus 1. A final recursive call sum of natural numbers of 1 with n equals 1 is made. This time, the base case is triggered, as n is equal to 1. The base case simply returns n, which is 1. The recursive call chain starts to unwind, and each returned value is added up along the way. 1 plus 2 plus 3 plus 4 plus 5 is equal to 15. Now, you can enter a different number and work out this code. Example 3. Write a function to display Fibonacci series using recursion. A Fibonacci sequence is the integer sequence of 0, 1, 1, 2, 3, 5, 8 and so on. The first two terms are 0 and 1. All other terms are obtained by adding the preceding two terms. This means to say the nth term is the sum of n-1, th and n-2, th term. Base case, if n less than or equal to 1, return n. We have two base cases. Fib of 0 equals 0 and fib of 1 equals 1. These base cases handle the scenario when n is 0 or 1, and they directly return the corresponding Fibonacci numbers 0 and 1, respectively. Write a function to display Fibonacci series using recursion. Now, look at the code. In line 2, the function recur_fibo takes an integer n as input, which represents the position of the term in the Fibonacci series that we want to find. In line 3, in the function, we have a base case to handle when n is less than or equal to 1. If n is 0 or 1, it means we have reached the base case, and the function returns n itself. In line 6, the recursive case is executed when n is greater than 1. In this case, the function returns the sum of two recursive calls, recur_fibo of n-1 and recur_fibo of n-2. These recursive calls are used to find the two preceding terms in the Fibonacci sequence. By repeatedly applying the recursive formula, the function calculates the Fibonacci number at position n in the series. In line 8, the user is prompted to enter the number of terms required in the Fibonacci series using the input function. In line 10, the program then uses a for loop to iterate from I equals 0 to I equals terms -1, inclusive. At each iteration, the recur_fibo function is called with the value of I. This calculates and prints the Fibonacci number at the ith position in the series. The loop continues until it reaches the last term specified by terms. For example, if the user enters terms equals 10, the code will generate the first 10 Fibonacci numbers and print them as 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. The Fibonacci series starts with 0 and 1, and each subsequent number is the sum of the two preceding ones. The function recur_fibo is called for each index position in the Fibonacci series, from 0 to 9, inclusive. When recur_fibo of 0 is called, it directly returns 0, which is the first term of the Fibonacci series. When recur_fibo of 1 is called, it directly returns 1, which is the second term of the Fibonacci series. For recur_fibo of 2, it reaches the recursive case and returns the sum of recur_fibo of 1 and recur_fibo of 0, that is, 1 plus 0 is equal to 1. For recur_fibo of 3, it returns the sum of recur_fibo of 2 and recur_fibo of 1, that is, 1 plus 1 is equal to 2. In the next step, 2 plus 1 is equal to 3. In the next step, 3 plus 2 is equal to 5. In the next step, 5 plus 3 is equal to 8. In the next step, 8 plus 5 is equal to 13. In the next step, 13 plus 8 is equal to 21. In the last step, 21 plus 13 is equal to 34. The sequence of function calls, following the recursion logic, calculates each Fibonacci number iteratively by summing the two preceding terms until the desired position is reached, giving us the Fibonacci series from 0 to 34. What do you mean by factorial of a number? The factorial function, symbol of factorial looks like exclamatory mark, says to multiply all whole numbers from our chosen number down to 1. Examples: for factorial is equal to 4 times 3 times 2 times 1 is equal to 24. 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1 is equal to 5040. 1 factorial equals 1. Factorial is not defined for negative numbers, and the factorial of 0 is 1. 0 factorial equals 1. The factorial of a non-negative integer n is the product of all positive integers less than or equal to n. It is denoted by n factorial and is defined as n factorial equals n times n minus 1 times n minus 2 times goes on times 3 times 2 times 1. Example 4. Write a recursive function to calculate the factorial of a number. Let's look at the Python code. The code defines a recursive function called recur_factorial of n that takes an integer n as input and returns its factorial. Here's an explanation of how the code works. In line 2, the function recur_factorial of n is defined with a single parameter n, which represents the number whose factorial is to be calculated. In line 3, inside the function, there's a base case that checks if n is equal to 1. If n is 1, it means we have reached the smallest possible factorial, and the function returns 1. In line 5, 6, if n is not equal to 1, it means the factorial needs to be calculated recursively. The function returns n multiplied by the factorial of n minus 1, which is calculated by calling recur_factorial of n minus 1. In line 8, the user is prompted to enter a number through the input function, and the input is stored in the variable num. In line 11 and 12, the code checks if the entered number num is negative. If num is negative, it prints a message indicating that the factorial does not exist for negative numbers. In line 13 and 14, if num is not negative, the code then checks if num is equal to 0. If num is 0, it prints a message indicating that the factorial of 0 is 1, as per the factorial definition. In line 15 and 16, if num is positive and not equal to 0, it calls the recur_factorial of num function to calculate the factorial of num and prints the result. Recursion in this code works by repeatedly breaking down the problem into smaller, simpler subproblems until it reaches the base case, n equal to 1, where it can directly return a value without making further recursive calls. The intermediate results are then multiplied together to obtain the final factorial. The factorial of 5 is represented as 5 factorial and is calculated as 5 factorial equals 5 times 4 times 3 times 2 times 1 is equal to 120. Now, let's visualize the recursive calls and calculations step by step. Recur_factorial of 5. Since 5 is not equal to 1, we proceed to the else block. We return 5 times recur_factorial of 4. Next step, recur_factorial of 4. Since 4 is not equal to 1, we proceed to the else block. We return 4 times recur_factorial of 3. Next step, recur_factorial of 3. Since 3 is not equal to 1, we proceed to the else block. We return 3 times recur_factorial of 2. Next step, recur_factorial of 2. Since 2 is not equal to 1, we proceed to the else block. We return 2 times recur_factorial of 1. Next step, recur_factorial of 1. Now, we have reached the base case where n is equal to 1. We return 1. Now, let's substitute the values back in reverse order to get the final result. Recur_factorial of 1 returns 1. Recur_factorial of 2 returns 2 times 1 is equal to 2. Recur_factorial of 3 returns 3 times 2 is equal to 6. Recur_factorial of 4 returns 4 times 6 is equal to 24. Recur_factorial of 5 returns 5 times 24 is equal to 120. So, the final result is 120, which is the factorial of 5. This visualization demonstrates how the recursive function repeatedly breaks down the problem into smaller subproblems until it reaches the base case and then combines the results to get the final factorial. Let's learn about binary search. Binary search is an efficient and fast algorithm for finding an element in a sorted list of elements. An example is finding your best friend's number in your contact list of 1,000 numbers. Binary search algorithms are also known as half-interval search. It finds elements by repeatedly dividing the array in half and then compare the middle of the division to identify in which division the element could be present. In order to implement binary search, we need 3 pointers, namely lower bound, upper bound, and a middle pointer. The division of a subarray is defined by lower bound and upper bound, whereas the mid-pointer value is compared to the value of the element that needs to be located. Binary search algorithm can be implemented in recursion method. The recursive method follows the divide and conquer approach to find the value's position. Let's see how binary search works. The binary search algorithm takes advantage of a collection of elements that is already sorted by ignoring half of the elements after just one comparison. These are the steps to implement binary search. To search an element, say val in a sorted array, suppose in ascending order, the val is compared with the middle element first. If the searched value, val, is equal to the middle value, then the index number and position number of this element is returned. Else if val is greater than the middle element, the second half of the array becomes the new segment to be traversed. Else if val is less than the middle element, the first half becomes the new segment to be scanned. The same process is repeated until val is found or the segment is reduced to the single element and still val is not found, in case of an unsuccessful search. This picture clearly explains how binary search works. If searched value is not found in the middle, and if the value is greater than the middle value, the second half becomes the new segment to be traversed. If the value is less than the middle value, the first half becomes the new segment to be traversed. For binary search, we have the following conditions. Condition 1. If the searched value, val, is equal to the middle value, then the index number and position number of this element is returned. Let's see an example. Val is the item to be searched. Val is the variable which holds the element to be searched. Val equals 40. Look at the first picture. A sorted array consists of elements 20, 30, 40, 50, 60, with index marked from 0 to 4. First index equals 0, last index equals 4, middle element equals first index plus last index divided by 2. Middle element equals first index 0 plus last index 4 divided by 2 equals 2. We found that the middle element is an index 2. Index 2 holds the value or element 40. Hence val 40 appears at index 2, which is highlighted in the second picture. So the search is terminated and the output is the position 40 occupies in the list, index 2. Condition 2. Else if val is greater than the middle element, the second half of the array becomes the new segment to be traversed. Let's see an example. Val is the item to be searched. Val is the variable which holds the element to be searched. Val equals 60. Look at the first picture. A sorted array consists of elements 20, 30, 40, 50, 60, and 70 with index marked from 0 to 5. First, we have to find the middle element of the whole array. Look at the left side middle red box. First index equals 0. Last index equals 5. Middle element equals first index plus last index divided by 2. Middle element equals 0 plus 5 divided by 2 is equal to 5 divided by 2 is equal to 2.5 equals 2. Middle element is an index 2. Index 2 is equal to 40. Hence val 40 appears at index 2. Value 40 is not the value to be searched. The value to be searched 60 is greater than the middle element 40. Hence we move right side to the second half of the array. Now look at the calculations on the right side of the middle red box. New search begins in the second half. Search starts at index 3 and takes the value from index 3 onwards. New first index equals 3. New last index equals 5. New middle element equals new first index plus new last index divided by 2. New middle element equals 3 plus 5 divided by 2 is equal to 8 divided by 2 is equal to 4. New middle element is in index 4. Index 4 is equal to 60. Hence val 60 appears at index 4, which is the value to be searched. So the search is terminated and the output is the position 60 occupies in the list, index 4. Condition 3. Else if val is less than the middle element, the first half becomes the new segment to be scanned. Let's see an example. Val is the item to be searched. Val is the variable which holds the element to be searched. Val equals 20. Look at the first picture. A sorted array consists of elements 20, 30, 40, 50, 60 and 70 with index marked from 0 to 5. First, we have to find the middle element of the whole array. Look at the left side middle red box. First index equals 0. Last index equals 5. Middle element equals first index plus last index divided by 2. Middle element equals 0 plus 5 divided by 2 is equal to 5 divided by 2 is equal to 2.5 equals 2. Middle element is an index 2. Index 2 is equal to 40. Hence val 40 appears at index 2. Value 40 is not the value to be searched. The value to be searched 20 is less than the middle element 40. Hence we move left side to the first half of the array. Now look at the calculations on the right side of the middle red box. New search begins in the first half. Search starts at index 0 and takes the value from index 0 and 1. New first index equals 0. New last index equals 1. New middle element equals new first index plus new last index divided by 2. New middle element equals 0 plus 1 divided by 2 is equal to 1 divided by 2 is equal to 0.5 equals 0. New middle element is an index 0. Index 0 is equal to 20. Hence val 20 appears at index 0, which is the value to be searched. So the search is terminated and the output is the position 20 occupies in the list, index 0. Let's see an example to write a recursive program to implement binary search in arrays/lists. Now, look at the Python code. Line 1. Define the binary _search function with parameters lst, the sorted list, low, the index of the lower bound, high, the index of the upper bound, and val, the target value to find. In line 2 and 3, check the base case. If high is less than low, it means the target element cannot exist in the list segment. In this case, return none to indicate that the element is not found. In line 5, calculate the middle index of the current list segment, mid-val, by finding the average of low and high and using integer division to get an integer result. In line 7, compare the element at the middle index, lst of, mid-val, with the target value, val. In line 8, if lst of mid-val is greater than val, it means the target value is in the left half of the list. So, perform a recursive call to binary _search with low unchanged, high updated to mid-val -1, and the same target value val. In line 9, if lst of mid-val is less than val, it means the target value is in the right half of the list. So, perform a recursive call to binary _search with low updated to mid-val +1, high unchanged, and the same target value val. In line 12, if lst of the mid-val is equal to val, we have found the target element. Return midval, which is the index of the target element in the list. If the function hasn't returned yet, it means the target element is not found in the current list segment. Continue the recursion with the narrowed list segment until the base case is reached. When the recursion ends, the function will either return the index of the target element or none if the element is not present in the list. In the example provided, in line 14, we call the binary underscore search function with the list 8, 11, 23, 49, 96, 100, and two different target values, 49 and 101. In line 15, the first call to binary underscore search with the target value 49 returns 3, which is the index of the element 49 in the list. In line 16, the second call to binary underscore search with the target value 101 returns none since 101 is not present in the list. Let's see the difference between recursion and iteration. Recursion is a programming technique where a function calls itself, whereas iteration is a programming technique where a loop repeatedly executes a set of statements. Recursion involves solving a problem by breaking it down into smaller subproblems, whereas iteration involves solving a problem by repeatedly executing a set of instructions until a specific condition is met. Recursion is often used when the problem can be naturally divided into subproblems of the same type, whereas iteration is often used when a sequence of instructions needs to be repeated multiple times. Recursion generally requires more memory space due to multiple function calls being stored on the call stack, whereas iteration generally requires less memory space as it doesn't involve creating multiple function calls. Recursion may lead to a large number of function calls, resulting in potential stack overflow if not optimized, whereas in iteration, no risk of stack overflow, as it doesn't involve function calls and less nested within other functions. Recursive solutions are typically shorter and more elegant for certain types of problems, whereas iterative solutions can be longer, but they may be more efficient for certain problems. Recursion may be slower due to the overhead of function calls and stack operations, whereas iteration is generally faster due to fewer overheads and direct control over loop execution. Recursion examples: binary search, calculating factorial, traversing tree structures. Iteration examples: for loop, while loop, iterating through arrays or lists. Some problems are inherently suited to recursive solutions, whereas iteration is often the default choice for many programming tasks. In recursion, base case is essential to avoid infinite recursion, whereas in iteration, loop termination condition must be carefully defined to prevent an infinite loop. Thanks for watching. Watch the upcoming videos. Using Python Libraries Part 1. Introduction, Module in Python, Importing Python Modules, Name Resolution and Module Aliasing. You can check the link in the description box below.